Okay, we'll begin. Are there questions? Okay, so if not, let me remind you of some of the definitions that we gave last time. So we defined the scalar perturbation as follows. We take and here we had h to the 4 over 2 phi bar dot square omega cube. So this quantity we called PR, that is the scalar power spectrum. Or no, we call it PR or PS, okay, doesn't matter. Okay, then we had this other quantity, sum over S, Hs of k tau, Hs of k prime tau. So this was 2 pi cube delta q k plus k prime. And then here we had 4 because the factor of 2 came from the sum. So 4h square over 2 omega cube, sorry, over m omega cube. So this one we call the tensor power spectrum. And then we define two more quantities, okay, the amplitudes of perturbation. Delta S square was defined as omega q over 2 pi square times PR. That was h to the 4 over 4 pi square phi bar dot square. And delta T square was omega q over 2 pi square times PT, and that's 2h square over pi square. And then we said that these quantities, delta S and delta T, are approximately omega independent because you don't see any explicit omega here. But there will be an implicit omega dependence, okay, small omega dependence, because this has to be evaluated at the horizon crossing time, and the horizon crossing time in turn depends on omega. Okay. So later today we'll try to see exactly how that dependence can be analyzed. Okay, but the first approximation we can take them to be omega independent. Okay, and that's what one calls the scale invariant spectrum. We'll also introduce another quantity, okay, the tensor to scalar ratio. So that R will be defined as delta T square over delta S square. That is 8 phi bar dot square over h square. And the point is delta S and delta T can be related to the observations in CMB, okay, which we'll discuss later. But from CMB measurement, we know what these objects are. In particular, we haven't observed delta T yet, but observation gives the following results. It tells us that R is less than 0.2. Okay, that means that the tensor to scalar ratio is small. Okay, maybe not too small, but at least less than 0.2. And delta S is of order 10 to the minus 5. Okay, this we have observed. The CMB fluctuation gives you direct information about delta S. That's of order 10 to the minus 5. And this tells us from this definition that R is delta T square over delta S square, the delta T square is less than of order 2 times 10 to the minus 11. Okay, all using natural units. Okay, basically you raise it to, you square it and then you multiply by r. Okay, so that's what gives you 2 times 10 to the minus 11. Now, on the other hand, delta t, okay, you see from this formula, okay, delta t depends on h. So this means that we can put a bound on h, okay, at the time of inflation. So 2h square over pi square is less than 2 times 10 to the minus 11. But what is h square? H square is v by 3. In the natural units, h square is 8 pi g over 3 times v, but 8 pi g you have set equal to 1. So this is v by 3. So v is the potential at the time of inflation. So this then gives you information about v directly. Sorry, h square is v by 3. Yeah, so this gives you, this implies that v is less than or equal to, let's see how to have pi square by 2, 3 pi square by 2 times 2 times 10 to the minus 11. That's about 3 times 10 to the minus 10. So we see that the tensor perturbation directly gives you information about the scale of inflation. Okay, because the value of the potential at the time of inflation. So if we do observe tensor perturbation someday, okay, we'll know precisely the energy scale at which the inflation took place. Okay, that gives you the value of the potential. So let me now translate this to the scale that you're familiar with. So if mi is the scale of inflation, the mass scale of inflation, then v, okay, v has a dimension of energy to the 4. So v is like mi square. In fact, that's the definition of mi to the 4. So then the previous bound basically translates to mi is less than or equal to, we had what, 3 times 10 to the minus 10, right? 3 times 10 to the minus 10 to the power 1 quarter. And then the unit, okay. So unit, recall that we are using reduced Planck unit. Okay. So in terms of the Planck unit, it's m Planck over square root of 8 pi. Okay, because instead of setting g equal to 1, we have been setting 8 pi g equal to 1. Okay, that's the convention that we used for calculating the tensor fluctuation, for example. Okay, so this is m Planck over 8 pi, and m Planck is 1.22 times 10 to the 19 GeV. So this roughly translates to about 10 to the 16 GeV. So in other words, the non-observation of tensor modes to this date tells us that the inflation must have taken place at a scale that is less than 10 to the 16 GeV. Okay, because otherwise you would have seen the tensor modes by now. Is this okay? Are there questions?
Can you say it again?
Yeah. So the fact that tensor modes have not been observed, okay, that's the origin of this bound, right? That r is less than 0.2. So this translates to this bound on V, right? And that in turn can be stated as a bound on the scale of inflation, mi, okay, by identifying mi as the fourth root of V. And that's the bound, mi is less than or equal to 10 to the 16 GeV. So the scale of inflation has to be less than 10 to the 16 GeV to explain why we have not observed the tensor mode so far.
What do you mean by scale? I mean, is it just
that's this definition?
Okay.
Yeah, so the mi is this definition, right? So scale roughly, okay, is that after the inflation has ended, If we assume that the reheating is efficient, then the whole energy density gets converted to radiation almost immediately, right? This is for efficient reheating. So then MI will be the scale of temperature, right? Because so that, but typically what will happen is that the reheating process is slow, okay, maybe slow, and it may take a while before the energy density gets converted to radiation. So in that process is getting diluted by the expansion of the universe. But this is the absolute upper bound on the temperature scale that would have reached after inflation. Okay, that even for efficient reheating, the temperature couldn't have gone above this.
Yeah.
Is this sort of form sensitive to the kind of potential we take?
No, so far this, we have not really said anything about the kind of potential we take, right?
In the previous page we did, right? When we said that h square is v by 3 sort of a...
No. This is just the fact that the Einstein's equation. Lambda dot over lambda square is 8 pi g over 3 times energy density, right?
Yeah, so we are taking the slow rolling constant sort of v.
Yeah. So because if you don't have the slow roll h, right, then of course it's not even de Sitter.
No, but like we argued earlier that we can even achieve slow rolling by some g times pi to the power alpha, where alpha is some greater than equal to quantity.
Yeah. So in that case, this v is like the v near the end of inflation.
Yeah. Yeah. Okay.
Where it's still, I mean, as long as the slow roll condition is satisfied, right, that means that the change in h over a Hubble time is small. That's the definition of slow roll, right?
Yeah.
So you can still define this v as near the end of inflation, because what happened early in the inflation really doesn't matter, because that gets wiped out, right? It's the last 60 folding that controls the physics that we see.
Yeah.
What you observe in today's horizon. Is this clear? Are there questions?
And the fact that we needed that 60 folding was also related to the potential being 10 to the 16.
Yeah, except that, I mean, that is not very sensitive. You can do it, rework out. I mean, if you go through the logic again, you can work out how much that 60 number 60 changes to something else, and you will find that that number doesn't change that much. Okay, if you take it to be at 10 to the 10 GeV, it's more or less the same. Because it's logarithmic, right?
Yeah. Okay.
It's log of a large number, right? So it is changed by a factor of 10 to the 6. We'll maybe change this by log of 6 or by 6, right? Log of 10 to the 6. So you'll find that it's not really, it doesn't change things very much.
Okay.
Okay, any other question? Okay, so next what we are going to discuss is a theoretical upper bound. On R. Now here, I should really put it in quotes because it's not a strict theoretical bound. There are ways to violate it, but it's based on certain reasonable assumptions about the potential. So for this, let's recall the form of R. Okay. R is given here, okay, 8 phi bar dot square over h square. So this I can rewrite as phi bar dot as square root of R over 8 times h. Okay. And now let's suppose, assume slow roll. Okay. So which means that the phi bar dot and h changes slowly. Okay, compared to h. Okay, so in time h inverse, the change in phi dot is small compared to phi dot, and change in h is small compared to h. Okay. And let's suppose that this is slow enough so that it remains more or less constant. Okay. Assume that remains more or less constant, or less constant during the last 60 folding. Yeah, you have to have at least 60 folding. Okay, so like it could be more than 60, but let's suppose that we just look at the last 60 folding. Okay. So let's look at write down the equation again. So you have the phi bar dot as square root of r over 8 times h. Okay. And you are assuming that the phi bar dot and h are more or less constant. Okay. So that means r is also constant, more or less, during the last 60 folding. So if we now calculate this integral, so Ti and Tf, so this is the end of inflation and this is the beginning, or instead of the beginning, you can take the last 60 folding, doesn't matter. So let's say take some time that before the last 60 folding, okay, so that at least 60 folding should be there. So this is will be given by according to this formula. Okay, if we assume that r is more or less constant during this last 60 folding, it's r over 8 times integral Ti to Tf h dt. Now this side is phi of Tf minus phi of Ti. This side, on the other hand, square root of h r over 8 h dt, that is n. This is the number of e-folding. Right? Because lambda is going as c e to the ht. So lambda of Ti over lambda of Tf is e to the h times Tf minus Ti. Okay. So this integral, okay, which is roughly h times Tf minus Ti, okay, is log of lambda of Ti by lambda of Tf, right? And that's what we had called the number of e-folding. So h times Tf minus Ti is log of lambda of Tf. So this is the number of e-folding and this is about 60. So this gives a relation, okay, that in terms of r, okay, how much phi would have traveled, how much phi would have changed during the last 60 folding, right, which you know must exist for the inflation to solve the problems that you want to solve. Okay. So if we now impose this condition that n is larger than 60, this implies that delta phi is larger than square root of r over 8 times n. Well, so far we have not done really much except for assumption of slow roll. Okay. But now we are going to put in that theoretical constraint, okay, that it's natural to put a constraint. Okay, it is natural to require that delta phi is less than 1. Okay. That means that the change in phi should not be of the order of the Planck scale. And the reason that this constant is put is the following. Okay. That for a generic case, okay, for generic potential, generic scalar field, quantum gravity corrections could correct the potential by terms of order inverse m Planck to the minus, say, n for n positive. Okay. Because typically quantum gravity corrections we expect to be small, okay. But small means they are suppressed by powers of m Planck, okay, because the 1 over m Planck is like the strength of quantum gravity. So this means that if you write down a general potential, okay, suppose you had started with some nice potential, okay, which is flat. Okay. So let's say V nice of phi. Then we expect that the quantum gravity corrections will give corrections of order m Planck to the minus n, and those will be typically of the form phi to the n over m Planck to the n. Maybe phi to the n plus 4, because it has to have dimension of mass to the 4. Okay, so this is the kind of correction we'd expect from quantum gravity. So these are higher dimensional operators. But you see that what this is saying is that when phi becomes larger than m Planck, then the quantum gravity corrections become large. So even if you start with a flat potential, the quantum gravity corrections will make it non-flat at a scale of order m Planck and higher. Would become large, destroying flatness. So because of this observation, for a generic case, it's natural to demand that the range over which the scalar field during inflation travels should be less than m Planck. So this is the reason. For demanding delta phi less than m Planck. Okay. But let's now see what it implies. Okay. So here you have seen the delta phi is larger than square root of r over 8 times n. Now we are demanding the delta phi should be less than 1, okay, in the natural units. So this implies that square root of r over 8 times n should be less than 1, since delta phi is larger than square root of r over 8 times n, or delta phi is of this order. And we demand delta phi less than 1. And now we use also the fact that n should be larger than 60. So this gives you that r should be less than 8 over n squared, that is 3600. Okay, that's of order 1 over 500. So this bound on r is what is called Lyth bound. And I should just add that this is natural, but can be overcome in principle. So essentially, to get out of this naturalness argument, we have to find some way to make these terms absent. Okay? You have to give some argument as to why these terms shouldn't be generated. Okay? And sometimes that can be done by assuming some approximate symmetry, okay, or by demanding some approximate symmetry of this potential. Okay? And there are some class of models, okay, with that property. Okay, one class of models is called the Axiom Monodramay models. Okay, where basically you think of the phi as an axion field, and that has there are other reasons to believe that that potential should remain flat even under quantum gravity corrections. Okay. So it's not that this bound cannot be violated, but it's in general this bound exists for a generic potential. Now this bound, okay, this is almost impossible to observe in current experiments, right? As I said, the current bound is 0.2 and the future experiments may improve it a bit. Okay. So this will make it impossible to observe R. To observe R, at least in the near future. So this means that if we do find a non-zero R, if we do observe tensor modes, it will put strong constraint on the kind of potential we can use for inflation. Is this argument clear? Are there questions?
So when we say that the mass scale of inflation of the potential is 10 to the 16, does that also mean that the mass of that scalar particle would be 10 to the 16?
Well, that's natural, but it's not necessary. Okay, sometimes it can be larger, sometimes it can be lower, because mass of the scalar particle is essentially depending on the curvature at the near the minimum, right?
Yeah.
So that could in general have a different value compared to the overall scale of the potential.
Yeah, I see. And like, suppose we have a normal QFT, normal phi square potential with m square term. This m is what would couple to gravity, right? If we were to include it in the Lagrangian.
Yeah, well, what will couple to gravity is the energy momentum tensor of this field, right? Which
Yeah.
you know about m, right? But as far as the field theory is concerned, it's the energy T mu nu that will couple to gravity.
Yeah, I was thinking that the effective potential would contain terms of this m, small m also, like the mass of the scalar.
But those are like the fluctuations of the scalar field. That's what you're talking about, right? See, if you look at the inflationary potential, V versus phi, okay, let me draw it this way. So indeed, when the scalar field fluctuates around the minimum, it's like a harmonic oscillator with frequency m. And that will produce certain energy density that the gravity will couple to. But in this region, the energy momentum tensor is basically coming from here, right, this height. So this doesn't have any direct knowledge about m. Okay, of course, everything is coming from the potential itself.
Yeah, but like the terms that you added there to the effective potential in the case of quantum gravity, when you said that there are some terms added which are suppressed by by negative powers of m.
Yeah,
Now,
m
uh,
plus.
that is present all over the space, like in the entire region.
Yeah, yeah. Because that's just a quantum field theory tells us that this is a term in the effective action, right? So that term has to be added for all values of phi.
Yeah, but what is the origin of that term? Does it come when we write something like the action for gravity in the
Yeah, it
Lagrangian?
will come from terms like this, for example, right? If you have phi, this is a graviton loop, say. Well, maybe I can draw a simpler picture. Like, say 2 phi's exchanging graviton, right? And loop momentum, of course, can become large. And the point is, as long as the loop momentum is small compared to m Planck, you can show that these couplings are of order 1 over m Planck, right? And this loop momentum is small, but when it becomes comparable, then this can give order 1 contribution. And now the point is, the more phi's you add, right? I mean, you can add, for example, couplings like this. You can easily check that in Einstein's gravity coupled to phi, there are couplings of this kind also, 2 phi's and 2 gravitons. So all these terms, right, will be contributing to the effective potential, that if you somehow integrate out the graviton exchanges, right, you get some kind of 6 phi coupling, which you can encode by saying that there is an effective potential for which is order phi to the 6. Okay? You can also add things like this. Okay, this will be an effective potential of order phi to the 8. And the point is that these kinds of terms, okay, will all be suppressed by 1 over m Planck. Okay, because these will get contribution from when the loop momentum is of order m Planck. And you can just do the power counting to see how many m Planck you have in the denominator and how many in the numerator, and you can show that basically these are suppressed by m Planck. So if you have a phi to the 6 coupling, okay, just from dimensional analysis, okay, because there is no other dimensionful parameter here, right? It will become 1 over m Planck square. Phi to the 8, okay, this is in 4 dimensions. Phi to the 8 will be 1 over m Planck to the 4, and so on.
Yeah, I was just like sort of hoping, I guess, that the mass of the scalar particle will also show up.
Yes, indeed. But those are absorbed in what is called renormalization. Okay, that's the observed mass of the scalar particle, like this.
Yeah.
So typically what will happen is that if you try to do this calculation explicitly, unless there is a symmetry that prevents the scalar forming light, this will also drive the scalar masses to m Planck square, m Planck. But then in the theory of renormalization, you say that, okay, that's not what I observed. Okay, the scalar mass is what you observe, okay, which is the result of the original scalar mass plus all these corrections.
Yeah.
Okay, so that's why you don't. Yeah, you should worry, but at least in a renormalizable theory, you don't worry about the scalar mass getting renormalized because that's the observed scalar mass. But once you have done up to phi to the 4, right, typically what will happen is that in higher order terms, you'll get corrections like this. Okay, up to phi to the 4, you can absorb into renormalization. Okay, in a renormalizable theory, because lambda phi to the 4 is a renormalizable coupling. And then if you assume that there is some kind of cutoff, okay, at the quantum gravity level, right, it could be string theory or it could be something else. Otherwise, if you don't have a cutoff, then these momenta can go to infinity, right? And these diagrams actually diverge if you try to do this. Yeah. Not these diagrams, but higher order diagrams will start diverging. Okay, these diagrams are probably finite in gravity, but higher order diagrams will start diverging. So those you say that, okay, there is a natural cutoff and you get corrections of this kind. So this, I mean, kind of analysis actually makes sense only if we assume that the theory has an ultraviolet completion, which means that the quantum gravity can be made to give a finite result somehow. Then this naturalness condition question comes in, that if you do assume that you have something like string theory where you get a finite result out of quantum gravity corrections, then unless there is a symmetry, you expect corrections of this kind in the potential. Is this point clear?
Yeah, I guess. Yeah. I mean, all we are saying that through naturalness, we are ensuring slow rolling.
Yes. So first of all, you don't even know why you have a slow roll potential in the first place, right? There may not be any field in the theory which has slow roll. Okay, in such a theory, you will not have inflation. But assuming that somehow we have arranged that there is a slow roll, that part of the potential gives you slow roll, then you have to make an extra effort to make sure that the slow roll condition holds over a range that is larger than M Planck.
Yeah.
That's all you are saying here. Again, you can say that once you have gotten slow roll in some range, we might as well assume that it holds for larger range, right? But I mean, typically when people talk about naturalness, you would like to show that if it holds for over a larger scale, right, then maybe there is some symmetry why it holds for a larger scale.
Okay.
Okay, and that's all we are saying here.
All right.
Any other question? So, for example, if we saw that if you take this half m square phi square, right? V of phi equal to half m square phi square, even the simple potential can provide inflation for some over some range. Over some range, phi I phi f, for small enough m. But you can easily convince yourself that if you now add to this a term like some constant times phi to the 6 over m Planck square, okay, you might expect that this term is small because you have an m Planck in the denominator. But in order for this to provide inflation, okay, it has to have a big range. And so one way is to make the scale of inflation small, okay, because this is what the Lyth bound gives, right? That if r is small, that means r is small means we had seen earlier that r directly controls the scale of inflation. So small r means that the scale of inflation has to come down. Okay? Then there is no inconsistency. Okay? You can go, you can travel distances large enough, okay, and there is no conflict. But if that's not the case, then a correction of this kind, okay, added to the potential, will violate the condition for inflation. Is that point clear?
Yeah. Also, just one last thing. This coupling sort of a thing that appears in front of these terms, it's always positive.
No, it could be negative also.
And that would
but presumably the whole potential should be positive definite, otherwise it doesn't make sense, right?
I mean, we would like that to happen, but
yeah, if it doesn't happen, then the model is unstable.
yeah, okay.
But as some of the couplings could be negative, that means there could be extra minimum of the potential other than at phi equal to 0. Yeah, but as long as it's bounded from below, we are okay.
Yeah, okay, fine.
Okay, any other question? Okay, so next we are going to define the spectral index, which has to do with the fact that those delta S and delta T that we introduced are not fully omega independent. So let's recall, we have this formula, delta S square is h to the 4 over 4 pi square phi bar dot square, and delta T is 2 h square over pi square. And this has to be calculated at horizon crossing, at T star. So we'll define the scalar spectral index. ns as 1 plus d log omega. So d log delta S square d log omega. So this 1 is just convention. Okay, that's the way it's defined. And nt is d log delta t square over d log omega. So these basically encode deviation from scale invariant spectrum. And if ns is constant, then this will imply that delta S square goes as omega to the power ns minus 1, right? And this will imply that delta t square will go as omega to the nt if ns and nt are omega independent. Okay, otherwise it's a more complicated dependence on omega. So what we are going to do is to now calculate this for inflation. Okay, are there questions? Okay. So the way to calculate this will be that we first convert this omega to time, okay, because the time omega determines the time of horizon crossing, and then we'll figure out how these quantities, okay, depend on the time. So recall the equation determining horizon crossing. T star, where the horizon crossing time, and that was omega inverse equal to lambda inverse h inverse, or omega equal to lambda h. So this essentially relates omega to time, because lambda changes with time, okay, and that's what fixes T star in terms of omega. But we'll not try to write down that relation, okay, that we have already written before. What we are going to do is to convert d omega to dt, okay, because so that the derivative with respect to omega, I can now translate to derivative with respect to time. So d omega from here is given by lambda dot h dt plus lambda h dot dt. So this I can write lambda dot is h times lambda h. So this is lambda h square dt times 1 plus h dot over h, I think. Lambda, sorry, h dot over h square. But this is small. This is small because we have already assumed slow roll condition, which means the change in h, okay, over 1 Hubble time is small compact to h. Okay? That's exactly this. So this is in fact part of the slow roll condition, that this remains small. So I can just approximate it by lambda h square dt. So this means that omega dd omega, so omega is lambda h, and dd omega will be 1 over lambda h square ddt. So this gives you h inverse ddt. So let's now calculate omega dd omega of log delta S square. So this is, so omega dd omega, you have already seen h inverse ddt. So h inverse ddt And now we are going to use the expression for delta S square, which was, because it's log, right, this is log. The constant part really doesn't matter. So I can just write this as h to the 4 over del t phi bar square. So this is h inverse times 4 h dot over h minus 2 phi bar double dot over phi bar dot. So this I'll write as 4 h dot over h square minus 2 phi bar double dot over phi bar dot. And now you recognize that this quantity h dot over h square we called the slow roll parameter minus epsilon. So this is minus 4 epsilon. And this quantity we call the slow roll parameter minus eta. So plus 2 eta. So this is a combination at horizon crossing at T star that gives the spectral index. So these in turn can depend on omega, because these epsilon and eta, if you remember, we translated it into the property of the potential, and these could change with time slowly. So these themselves, the spectral index, okay, could depend on omega itself. Okay, is this clear? Are there questions? Okay. So let me remind you of the definition. So Ns was 1 plus this. So this gives an expression for Ns. I'll just write this as 4 epsilon star plus 2 eta star. So the star just reminds us that this has to be calculated at the time of horizon exit. And a similar analysis can be done for the delta t. Okay, let's do this. So omega dd omega of log delta t square. This will be omega or h inverse d dt of, this is just h square. Okay, again the constant part I'm ignoring. Sorry, log h square. Log h square. So that's h inverse times 2h dot over h. So that's minus 2 epsilon. So this gives the nt equal to minus 2 epsilon star. So this shows that Ns and Nt gives us direct information about V of phi. Because any knowledge that we can get from the CMB on Ns and Nt, we can get knowledge that tells us about the form of the potential near horizon exit. Now Nt has not been observed. And Ns has been, okay, Ns is a little less than 1. This has now been observed. Okay, so not only we know that the CMB spectrum is scale invariant, or approximately scale invariant, we also know that there is a deviation from scale invariance that is encoded in NS. And this you can in fact show is consistent with these minus signs over here, because typically for a potential where the potential is going down as a function of time, this quantity will be negative. Okay, so the fact that NS is less than 1 is consistent with the fact that these perturbations come from inflation. Okay, any other question? Any question? Okay, so next let me give some physical interpretation of this perturbation R, because that will play an important role in our analysis. For the tensor perturbation, there is in fact not much confusion, because the tensor perturbations don't mix with anything and they are clearly fluctuations of the graviton. But R, okay, as we have seen by gauge transformation, you can transfer R to various fields. So let me remind you that R was a combination of psi plus H over del T phi bar times phi tilde. And let me also remind you how R appeared, how psi appeared in ds square. Okay, later on maybe I'll write down the full metric, full part of metric. ds square is minus dt square plus lambda t square. Maybe I write down the full metric now itself. So ds square is minus 1 plus 2 phi, this is capital phi, dt square plus 2 lambda I'm writing only the tensor perturbations. Sorry, the scalar perturbations. Well, I'm not sure if I had written the factor of 2 here or not. Maybe I did. Okay, just check this.
Yeah.
Yes, go ahead, please.
Up till now in our analysis, we are considering only scalar and tensor fluctuations, but there's no reason why there could not be any sort of vector fluctuations also, right?
Yeah, that could be. If there is a massless vector field at the time of inflation, it could produce fluctuations.
Do we observe that?
No, no. So I mean, in the CMB, so far we have only observed the scalar perturbation.
So, I mean, does it say that the field, the field that we are considering for inflation should have been a scalar field? It could not have been a vector field.
In a sense, yes. I mean, even otherwise, I mean, driving an inflation by vector field would be difficult, right? Because vector fields typically don't come with potential. Right? If you have a nearly massless vector field, you have to have gauge invariance. So what could happen is that there may be inflation driven by a scalar field, and on top of that, there may be massless vectors present, for example. Okay, and it could fluctuate. But then the next question would be that whether those fluctuations, how do they affect what we see today? Right? I mean, that part, in fact, we have not discussed so far. Right? We will see how these fluctuations in R, for example, affect today's discussion, today's CMB spectrum. Right? How the fluctuations in the tensor fields affect today's CMB spectrum. So similarly, we can ask how the fluctuations of the vector fields, I mean, if there is a massless vector, how they would affect CMB spectrum today. Right? And if there is an effect, we should have seen it. Right? And but it may also happen that the vector field coupling is such that you will not have any effect on CMB spectrum today. Right? Even in that case, even if there is fluctuating vector field, it will have no observational consequence. Yeah, but you are certainly right that if there is a massless vector at that time, it would have fluctuated and you could quantize it exactly in the way we did for the scalar and the tensor. And you will get two modes of that.
Yeah.
Okay. Any other question? Okay. So here remember that we had a gauge invariance and R was a gauge invariant object. So the gauge transformation involved this time translation, the xi naught symmetry. Okay. So that was phi tilde goes to phi tilde minus xi naught del t phi bar, and psi goes to psi plus h psi naught. Right? And that's why this combination was gauge invariant. Now let's look at the two gauges. Okay, in the B equal to E equal to 0 gauge, here the dynamics, as we discussed, okay, namely Einstein's equation, sets also phi equal to 0 and psi equal to 0. Okay, the gauge invariant statement is that some appropriate combinations of phi and E and B are set to 0 by dynamics, but that reduces to phi and psi equal to 0 if B and E are 0. In this case, R gets contribution only from phi tilde, scalar fluctuation. Now, scalar fluctuation means what? That as the inflaton is rolling, as phi is rolling down the potential, in some region, okay, phi may be a little ahead. In some other region, the phi may be a little behind. Right? That's what fluctuation means. Okay, so this means that phi is ahead in some region and is behind in some other region. And this ahead and behind refers to is measured with respect to the background, the average value. Now, if phi is ahead in some region, what does it mean? This means that here the inflation will end early. Here, inflation ends late. If inflation ends early, then the temperature starts dropping early in these regions. Right? Because the temperature, once the inflation ends, then you have this whole process of converting energy density to radiation, okay, by this reheating process, and then the temperature starts falling by the expansion. So here, T starts falling early. Here, it starts falling late. And then this fluctuation, the early fall of temperature means what? That in some region, then temperature will be larger than the others. This means in some region, T will be larger. Okay, if it starts falling early, then it should be smaller. and other regions T will be larger. Okay, so there is temperature fluctuation at constant time slice. Okay, that's the definition of time you are choosing here. But this by itself is not directly translatable to CMB fluctuation, because if the temperature is larger in some region, that means that the recombination will take place a little later in that region, right? Because the recombination requires the temperature to drop to a certain value. So it's not that this information can be directly translated to CMB fluctuation, but what one can show that by doing this, you can eventually translate this to CMB fluctuation. Okay, so this can be eventually translated to fluctuations in CMB temperature. Okay, and that's what we'll try to work out. Is this point clear? Well, this is one way of saying why fluctuations in R will eventually translate to some effect on CMB. But you could also take another gauge. So we could also choose a gauge. Phi tilde is 0. So if phi tilde is 0, this means what? Okay, let's look at R. Okay, the expression for R that we had. Psi plus h over del t phi bar times phi tilde. So R will not be now be equal to psi. So now the fluctuation in R comes from psi. Now, what is psi? Psi is the degree of freedom of the metric, right? You can see from here, psi is this degree of freedom of the metric. So I should have said during the last discussion that when in this gauge, the metric has no fluctuation, right? That's the way you have chosen, because B equal to, once you choose B equal to 0 gauge, dynamics sets phi and psi equal to 0. So the metric is just the background flat metric. Okay, there's a fluctuation in the metric. Only the scalar field fluctuates. But now you see that in this new configuration, it's this psi which fluctuates. Okay, so let me write this. So ds square is minus dt square plus lambda t square 1 minus 2 psi dx square. Okay, that's the form of the metric, because if we just have the psi fluctuation, okay, then we forget about this. We have 1 minus 2 psi. Is this clear so far? So in this gauge, phi is uniform. This means that the inflation ends everywhere at the same time. That is the definition of time that we are using. Okay, that's what I mean by choosing a particular gauge. That we define time so that the inflation ends at the same time everywhere. So this means that no temperature fluctuation of the kind that you saw. But the metric fluctuates. So the spatial metric, okay, is this up to this lambda t square factor. Okay, it's dx square times 1 minus 2 psi. Okay, so forget about the lambda t square. Let's look at this part of the metric. Okay, so the spatial slice is not flat anymore. In the earlier gauge, the spatial slice was flat because this part of the metric was as dx squared. Okay, now that's not the case anymore. There is a 1 minus 2 psi. And I can leave it as an exercise to check that if you calculate the Ricci scalar, for the spatial metric, this is proportional to, I think, this three-dimensional Laplacian on psi, which in momentum space just becomes k squared times psi height. So now the fluctuation that we are seeing is in the fluctuation of the three-dimensional space-time metric. So while the temperature is uniform, okay, because the inflation ended at the same time everywhere, the three-dimensional metric fluctuates. And this in turn affects the CMB temperature. This fluctuation of the spatial metric affects what we observe as CMB temperature. Okay, again, this is something we'll try to discuss later. Okay, how this is related. So what this is showing is that the same quantity, same fluctuation can be described in many ways by choosing different coordinate system. But the physical quantity, that is the fluctuation in R, okay, that's not going to change. And ultimately, what we observe in experiment is controlled by the fluctuation of R. Okay? It doesn't matter which gauge you choose. So what we'll try to do is to try to see how this R, this fluctuation in R, evolve as a function of time, because ultimately we have to start from the horizon exit. We know how our R fluctuates at the horizon exit, okay? And you have to evolve it up to the time of last scattering, because that's where CMB is coming from. So our first task is to study how R evolves from T star to TLS. And then study its effect on CMB temperature. Okay, how to translate this? Even after I found R at the time of last scattering, we have to do some work to figure out, okay, how exactly it affects the CMB temperature. This part can be done classically. Okay, we'll see later. This part is simpler, in fact. This from our earlier arguments should be simpler. For omega, which remain outside the horizon till TLS. Okay, then we had argued that the microscopic physics will not affect this evolution. But again, that we'll see as we do this evolution. Okay, it will be simpler when certainly when this is true, but you can also do it, analyze this when this is not true. Any question?
So, do we expect these fluctuations? I mean, they have grown, right? By a factor of h square by omega. They'll grow during inflation. The quantum
Yes,
fluctuation will grow over time.
they'll grow, but they'll eventually reach a asymptotic value, right?
Yeah, some value. Do
Yeah.
we expect that value to be comparable or like larger or smaller than the thermal fluctuations we usually have? Like we will have thermal fluctuations below the omega scale, right?
Yeah. So thermal
So
fluctuation during inflation or after inflation, you are saying?
after inflation,
Yeah.
in the radiation era and all, below the omega scale, we'll have those.
Yes. But
So
we'll,
that will be the inflation correlations.
yes, those we'll study, right? So basically what you are saying is that, let me draw the diagram again. That if you plot this lambda inverse H inverse versus T, we had this plot, right? And imagine that this is TLS. So if our omega is something like this, okay, this is our omega inverse, then during this time, the T re-entry, in this interval, the microscopic dynamics can actually affect the perturbation. So we'll study this. Okay, how the microscopic dynamics affects the perturbation in this interval. But for perturbations here, that will not happen. There we can simply classically evolve this all the way to this point and we get a simple answer. So this is the part you are worried about, right?
Yeah, I was saying that this part will sort of dirty the earlier part in the sense that the earlier correlations will get affected by this. Now,
Yes.
typically, when one, I mean, although this is not true since there is a different field here, there are different fields, but typically classical correlations are much larger than quantum correlations. But since and at that side things have been expanding and growing and I don't know what all is happening, but like that will that be larger than this part?
No,
The
it will affect, it will have a strong effect, okay? But it will be determined by this part. Okay, we'll see. Okay, it will certainly have a strong effect. The microscopic physics in this region will have a strong effect. So the CMB spectrum, okay, maybe I can just plot. This is a plot not in the omega space, but in the what is called the angular momentum space, but it doesn't matter. Okay, so basically you will have a nice growth like this, okay, and then there is the oscillation. So all of these will be produced by this physics. Okay, this is the part that's here. Okay, that's nice and smooth, and this can be calculated reasonably simply. But all of these can also be calculated. And when people now compare inflationary prediction to the actual observation, they fit all of these. So we'll see that the effect of this part, right, is to produce all these oscillations. And you can see that this is a big change, right? It's not that there's the continuation of this.
Yeah.
So if you call this a big effect, indeed the effect is big, okay, for the microscopic dynamics on this evolution of the perturbation.
Yeah. Okay. Yeah.
Okay, any other question? Okay, so let me just say in words the way we will proceed. So the step one is just a classical evolution. And this has to be done, of course, not just in the inflationary phase, but the whole intermediate range of radiation and matter dominant phase. So the way you are going to set it up is by solving Einstein's equation. Including fluctuating source terms. T mu. In general, if you work in a general gauge, right, then there is a fluctuation in phi tilde, fluctuation in the metric. So the phi tilde fluctuation will produce some fluctuation in T mu nu. So you set up the equation as some fluctuation of the metric on one side. That will involve, for example, the metric degrees of freedom, okay, and then the fluctuation in the scalars on the other side, which will formulate as T mu fluctuation, okay, not scalar, because eventually scalar disappears, right, and it transfers its energy to T mu. So the general equation that we want to solve is T mu on the right hand side and the Einstein's R mu nu minus half R G mu nu on the left hand side. The initial condition, of course, is controlled by the scalar, because T mu nu to begin with was coming from the scalar. So we'll solve this to linear order, okay, because the fluctuations you know are small, right? Even at the time of last scattering, it was like 10 to the minus 5. So linearized perturbation is good enough. So we'll characterize. So first of all, we'll characterize this. Okay, we'll just write down a general form of this. So this will be like T bar. There will be T bar mu nu plus T tilde mu nu. Okay. And we'll again decompose this into scalar, vector, and tensor perturbation. Okay. And solve separately for the scalar, vector, and tensor perturbation. Okay. And in that process, we will not assume that the universe is cosmological constant dominated, because we want to evolve all the way, okay, even during this region. And that will help us go all the way up to this point. Okay, and then you have to understand what happens beyond this. Okay, but we will see that what happens beyond this is somehow already encoded in the equations that we'll get by looking at these fluctuations. Okay, so maybe I'll stop here today and continue next week. Are there questions?
So this Lyth bound was solely coming from the assumption that or V5 this potential should not be involving any quantum gravity.
Potential doesn't involve quantum gravity effects. Well, the point is we did take into account the gravitational fluctuations. The tensor perturbations did come from quantum gravity effects, right?
No. This Planck effect. I mean, we assume that like in the assumptions, we wrote four assumptions.
Yes.
And we wrote that V5 should not be larger than Planck.
Yes, that is true.
So, and if phi goes beyond Planck, we'll have some corrections in V5 from that.
Exactly.
Region.
Yeah. So the question is that this assumption that V5 should not be larger than Planck, that's a reasonable assumption. But is it tenable, right? You may imagine that there is some approximate symmetry which makes it tenable for a certain range of phi. But if you are claiming, if you are demanding, if your situation demands that it should be tenable for a much larger range of phi than M Planck, then you need spatial symmetries to ensure that. Right? And that's all this Lyth bound is saying, that for a generic potential, it's not tenable to have this nearly flat potential over such a large range of phi. If you take that as your assumption that potential shouldn't be larger than M Planck to the 4, then within that assumption that this is hidden.
Yeah.
So it's a question of what is natural assumption, right? I mean, as you saw, this using this m square phi square is a natural potential, right? So you might say, okay, let's say if it works for you with m square phi square, then it works. Except that we have to assume that the potential remains m square phi square for a large range of phi, right? Including when phi becomes larger than m Planck. And that is not a very natural assumption, right? Unless there is some additional symmetry that makes that happen, you don't expect that to happen. Right? And that's essentially the point of this argument.
Okay.
Is that clear?
Yeah.
Okay. Any other question? Okay, so if not, I'll stop and then we'll continue next week.